All right, guys, let's finish up our discussion, our beginning of our discussion about this idea of linkage, right? The idea that the binding of one ligand to a macromolecule, or a protein in our case, is thermodynamically connected to the binding of another ligand, right? Inextricably, as we talked about in this schematic that I went through during our last discussion, right? Now, you guys may or may not know that this idea of thermodynamic linkage, the way in which different ligands are thermodynamically connected to each other by how they interact with the protein, is inextricably, or is directly connected to, or is the basis for this really fundamental idea in biology known as allosteric control. And this is the idea that the binding of a ligand to a protein can influence properties of that protein conformationally, dynamically, right? And then adjust how that protein behaves in some other part of the protein, or how another ligand interacts with it. That idea, that sort of like allosteric modification of function, is really key to understanding so much of basic biology and biochemistry. It's also key for understanding oxygen transport by hemoglobin, right? Which is sort of the key subject that we're discussing here, with hemoglobin as our fundamental example. One of the reasons I think I mentioned before that we use it, or I'm using hemoglobin as this example of demonstrating things about linkage and allostery, is that hemoglobin was the first complex allosteric system that was examined in any significant detail. It's been studied for well over 100, 120, 130 years, 40 years, something like that now. The basic ideas that have been worked out for hemoglobin can be applied with modification in some cases, depending upon molecular complexity, to virtually every other allosteric system in existence, right? So the basic principles that are worked out for hemoglobin are just widely applicable to understanding allostery in so many other basic systems. And another interesting aspect of it, there are elements of how this works, oxygen transport or allostery in hemoglobin, that people are still arguing about to this day. All right, so let's turn back to this question then of oxygen transport by hemoglobin, right? And that's sort of general conceptual idea, or the problem we're trying to solve. Remember, the physiologic problem that hemoglobin is designed to solve is that we need a protein that can pick up oxygen in the lungs, right? And then after being transported to the periphery, can let go, right? Really well in the peripheral tissues, right? And the question is, how do you build a machine that does this, right? Fundamentally, right? So it's a good place to start is to think back to the structure of how these molecules work, the globins work. Specifically, we go back and we think about the one protein I've introduced to you in some detail, and that's myoglobin, right? The simplest possible member of this globin family of proteins. It's a monomeric protein, as you guys hopefully remember, right? It's almost completely alpha helical. It's about 16 kilodaltons in molecular mass, right? So it's about 16 kd in mass, right? It's almost totally alpha helical. And you remember, of course, we have this prosthetic group right here in this hydrophobic pocket. It's got protoporphyrin 9, that heme, this tetraperol group with that iron atom right smack in the middle. And if you remember, we have on the one side of the heme, one of those octahedral coordinate positions, we have a histidine from one helix, so-called F helix, that is coordinated on that above plane coordination position, right up in here. And then on the other side, we have a histidine from the G helix, and there's a little space in there. It's the perfect spot for an oxygen molecule to bind to that remaining coordinate position to the iron atom above the plane of the heme, right? And myoglobin is just outstanding at binding oxygen. This protein is very tight binding of oxygen. It's really, really good at it. But it turns out that property, the fact that it binds oxygen really tightly, and the way in which this molecule is made, it makes it a terrible transport protein. To understand why, consider this. So remember, myoglobin, right, is a single site, simple ligand binding molecule. So we could write it down something like myoglobin plus oxygen would give us myoglobin bound to oxygen. And that's more or less exactly what you would expect, whoops, oh shoot, for a simple system like I just showed you, right? It binds one ligand, it's good, right? So here is that myoglobin binding curve as a function of partial pressure of oxygen. And indicated here in this red stripe, that's arterial, that's the partial pressure of oxygen in arterial blood, right? In the lungs, essentially. Here in this blue stripe is the partial pressure of oxygen in peripheral tissues, basically in venous blood, right? See the problem? So myoglobin will happily, beautifully load up with oxygen at arterial pressure, but look what happens over here at venous pressure. It won't let go, right? The affinity is so high that even at venous pressures, it still's holding on to 95% of the oxygen that it bound. It won't let go. It's useless, right? If your oxygen transport system from your lungs to the peripheral tissues was built around a system that looked like this, you're dead. It's not going to work. You're like, oh, okay, well, that's easy. All I got to do is I just got to weaken it. All I've got to do is take that binding constant. Oops. Uh-oh. There we go. I lost all I've got to do then is take my binding constant. Oh, come on. That I had written here and lost. Right? My KD, and I just make that smaller, right? Wrong. It won't work, right? Here's why. If you look right down here, here's what that would do. Here's a weakened myoglobin. Remember, binding the simple single ligand binding system is a hyperbolic function of the ligand concentration. Look what happens when you just dial down the affinity, right? Okay, over here, arterial pressures, oh, it's letting go now. That's great. This is really good, right? We can make it unload 40, 60, unload 60, 50, 60, 70%. Here's the problem. See the problem? Problem is now we can't load it anymore, right? We've compromised the ability to load the protein by 40%, something like that. At the concentrations of protein you need in an erythrocyte to get enough oxygens in those peripheral tissues, if you had a protein that behaved like this, you couldn't put enough protein in them for this to work. The solubility, you go blow right through the solubility limit and it's not going to work. So the problem now is you fundamentally cannot build a good oxygen transport protein that uses a simple hyperbolic dependence of the saturation on the ligand affinity. It's an unassailable, undeniable consequence of the uncompromising mathematics that describe this kind of simple single site ligand binding. So what do you do, right? Basically, what you need is you need a protein that behaves a different way, right? So if there's the hyperbolic binding curve of myoglobin, you need a protein that could sort of know when the oxygen concentration was low and let go. And then kind of also know when the concentration was high and switch its affinity and now bind it really well. You need something that responds non-linearly to that oxygen concentration. You need a molecule with a built-in ambient O2 sensor. How do you build a molecule like that, right? You got no microchips. You can't rely on, fancy circuit design or something like that. That sensing function has to be built into the structure and functional chemistry of how this molecule works. So the question is, how do you do that, right? And of course, evolution is amazingly good at finding solutions to problems like this. And the solution was to take the same basic structure of that myoglobin molecule, that same alpha helical, roughly 16 kD protein, change up the sequence a little bit, retain the fold of the hemoglobin and myoglobin monomers is virtually identical, change up the sequence a little bit, and create two different variants of that basic myoglobin fold, so-called alpha subunit and beta subunit of hemoglobin, and put them together here as sort of a dimer. Then put two of those together to form this hemoglobin heterotetramer. And so what you see, of course, in the hemoglobin heterotetramer is that each of these monomers has an associated porphyrin, right? So we've got 4 binding sites that work basically the same way as that myoglobin binding site I pointed out before. There are 2 histidines. One is directly ligand into the iron in the heme. The other, there's a little gap between the histidine and the G helix and the iron where the oxygen snuggles right in. But now we can transport 4 of these guys, right? Okay. But just binding them the way myoglobin does isn't going to work based on what we just went through, right? Okay, so the question now then becomes, how does hemoglobin do what it needs to do, right? And the answer is that hemoglobin binds oxygen in a concentration dependent way. Its affinity effectively changes as a function of the ambient oxygen concentration, or put more correctly, it changes as a function of the amount of oxygen bound, right? So some of you guys may remember this. So here we are over here at venous partial pressures, right? Here's the hemoglobin, right? It's maybe about 50% saturated, maybe a little bit less, depending upon other constituents of the solution that the hemoglobin's in. This can be driven down even lower. And then as we get up to arterial pressures, look what happens. That binding curve does that little nonlinear thing, and right up here, we now have nearly fully saturated hemoglobin. So across this, 2.5 fold, 3-fold, right, 3-fold range, so 3-fold range in partial pressure, hemoglobin can dramatically change its effective affinity for oxygen and do exactly what we need, right? Which is amazing, right? We got a narrow range of ligand concentration, big change in apparent affinity. So if you look at that curve, it's going to look a little familiar to you, right? We've seen that before. Specifically, we've seen that sort of nonlinear sigmoidal shape when we talked about cooperativity in protein folding. The idea that the interactions that start to hold a protein together are linked to each other and they non-linearly cascade, right, as they sort of come together to make well-folded globular proteins behave kind of like a unit, right? They don't exist in isolation. They're all built on top of each other and they're all linked thermodynamically to one another. This is the same basic idea. The binding of each oxygen influences, each oxygen atom to that hemoglobin tetramer influences the next one's binding, right? So over here, say, in high concentrations of oxygen, if you had fully unsaturated oxygen, binding that first oxygen, maybe it's a little hard. Once you get it on, the next one's easier, and then easier and easier and easier, right? So the affinity is high. Going down here, right, it goes the other way. Getting that first oxygen off maybe, a little harder than you might like, but once it's off, that next one's easier, and then so on and so on. It's the same kind of idea, the thermodynamic linkage between these different interactions, and the way in which they're coupled up gives you this nonlinear response. And exactly how that works, we will start exploring in the next lecture.